Well, howdy, y'all. I hope you ain't getting too bored with all the social distancing. Anyway, I'm sure you have plenty of physics lectures to digest. Maybe you have a guitar or some other instrument to play in between. So I'm going to give you another lecture today. This is lecture 5 of Thermal Physics and Statistical Mechanics. And on this lecture, we'll continue with our discussion of ensemble physics. Last lecture, we discussed the canonical ensemble, and we derived some properties of a spin system. In particular, we finished up with the heat capacity for a spin system. I'll discuss that a little bit more, and then we'll move to fluctuations in the canonical ensemble, and then on to the grand canonical ensemble. So at the end of last lecture, we finished up by calculating the heat capacity for a system of localized moments, that is paramagnetism of localized moments, assuming non-interacting spins. And we found this form for the heat capacity. Here, little CV is the heat capacity per spin. And it had this, and if we considered the case of, for simplicity, we considered a spin 1/2 system, and we found this form, this function for the heat capacity per spin. And we decided to plot this in terms of this variable x, which was kBt divided by magnetic energy. That magnetic energy is the G factor, which is usually about 2 times the Bohr magneton times the magnetic field. And so you can think of this x as the ratio of thermal to magnetic energy. And here I've plotted that. I've plotted little CV versus this x, which is kBt divided by the magnetic energy. And I've normalized the heat capacity by Boltzmann's constant divided by 2. So this on this y-axis is dimensionless, and this is dimensionless as well. And so up here is high temperature, this is low temperature. And at the end of the lecture, I ask you if you understood physically why it goes to 0 at both high and low temperatures. Well, this type of behavior at high temperatures, that is heat capacity going to 0, is typical of systems like spins where there are only a finite number of energy levels. That's easy to understand. If you look at the mean energy of one spin, and the general expression we had was this, if you look back at the last lecture, and you plot that as here I plotted that as a function of kBt over the magnetic energy, then and I've done this actually for several different spins, going at 7.5, 1, 1/2, and if you see what's happening here at high temperatures, that you can't actually put more energy into the system because the system's completely randomized. It's completely, distributed among all the states at very high temperature. And therefore, you can't increase the energy at all up at high temperature because of the finite number of levels that are all saturated. And of course, the heat capacity is the derivative of this mean energy. At low temperature as well, you have a similar effect. That is that the mean energy saturates down at low temperature as well. And that's because at low temperature there's an energy gap, this magnetic energy, for excitation of a single spin from the ground state. And so if the temperature is much lower than that, you're just not going to have any excitations up into any of the excited states. And so this mean energy becomes flat there, the derivative of 0. And of course there's some maximum slope here in the middle, right? So that's what's going on. And this peak in the heat capacity arises whenever there's a gap to excitation. Here it's the magnetic energy. And you'll see it in the literature called the Schottky specific heat. Okay, well, let's move on now. And what we're going to do, we're going to continue with the canonical ensemble, and we're going to talk about fluctuations in the canonical ensemble. Now, with the canonical ensemble, it's quite easy to compute fluctuations in dependent variables. So, for example, let's consider fluctuations in mean energy. The mean energy is given by this bracket U. Of course, it's just the sum over the states with the probability of the state times the energy of that state. And we write that as 1 over Z, where Z is the partition function times this sum. And of course, the partition function is just the sum of these terms. Now, the way I've written it here, I just want to make a note that the sum over I here in this derivation includes all the energy levels of the whole system. So we could even be referring to a system with n components if we wanted to. It's just that the I goes over all the levels. And that's all we need for this derivation. Because what you can see is that this term, if you look at all the terms here in this calculation of the mean energy, these terms here, you'll find that they can be written as the partial derivative of this exponential term with respect to beta, with a minus sign, of course. That's pretty obvious. And so it's very clear that you can write the mean energy as, which is this expression quite explicitly. You can write it as the negative partial derivative of the partition function with respect to beta times 1 over z. Or in other words, the mean energy can be found just from the partial derivative with respect to beta of the logarithm of the partition function. So in many cases, in some cases that is, some simple cases, you can find an explicit expression for the partition function which is quite simple, and you can then find the mean energy this way. So we actually did that in the last lecture. Well, it's quite easy to see that you can also find the mean or expectation of the square of the energy, that is, and we write that as bracket u squared here. If we write it out explicitly in terms of all the terms, it's just the sum over the energy states of the energy squared with this the probability here and the normalization. And you can see that's 1 over z times the second derivative of the partition function with respect to beta squared. Okay, well, we could also differentiate the mean energy, the expression for the mean energy, that is this expression or that expression, and we get these two terms, and we recall, well, this term is just minus times this, minus this term is just the mean squared energy, and this term we recognize as the square of the mean energy, right? So we write it like this. And that's just the negative of what we would typically say, we typically call the mean square variation or the mean square fluctuation of the energy, or the variance of the energy, right? So this, and we'll call that sigma u squared instead of writing this rather cumbersome thing. So basically we see that this is equal to the negative derivative with respect to beta of the mean energy. Well, we see this derivative with respect, derivative of mean energy with respect to beta, and that makes us think, well, there's the specific heat, right, which is a derivative of the mean energy. It's just the derivative with respect to temperature, like so. So we could see that actually there's a relationship between the variance, the mean square fluctuation of the energy, and the heat capacity. Because we know the relationship between temperature and beta, beta is 1 over kBT. So if we use this identity, we can go from a derivative of temperature to a derivative of beta. Basically, the partial with respect to temperature is 1 over kBT squared of the partial with respect to beta. And that allows us to write the heat capacity as 1 over kBT squared of the derivative with respect to beta of the mean energy. So we've actually related the heat capacity to the fluctuations in the energy through this expression. In other words, the fluctuation in the energy is actually kBT squared times the heat capacity, or vice versa if we want to write it the other way. Now, this actually turns out to be very useful in computer simulations. If you're simulating the canonical ensemble for some arbitrary system, and you simulate it at constant temperature, then you can observe the energy fluctuating during this run. Usually use some Monte Carlo program. It's called Monte Carlo. There's other ways to do it. And if you monitor the energy, you'll see it fluctuating. And if you measure the variance of the fluctuations, you can actually obtain the specific heat by averaging over time this variance that you observe in the simulation. Well, alternatively, you can get an approximation of the specific heat by running your simulation at two different temperatures. In that case, the specific heat would be basically the difference if I run my simulation at some temperature T plus some small delta T, and then I run it again at T minus delta T, and I look at the mean energy. Instead of looking at the fluctuations, I look at the difference in these mean energies when I run the simulation at two different temperatures, divide by 2 delta T. I can also estimate the specific heat that way. And if these two estimates do not agree, then it probably means your simulation hasn't run long enough. So that's actually a way to, if you're actually doing simulations, it's a way to check that you've run the simulation long enough to get consistent results. Well, let's suppose we had a system that's comprised of n identical subsystems. Once again, we have, by definition, the heat capacity. It's related to the partial derivative with respect to temperature of the mean energy. And in the case of a system with n identical subsystems, we know that this mean energy has to scale linearly with the number. That is, it has to be proportional to n. So we see that this variance, which goes like the fluctuation in the energy squared, has to go like n, right? Because it goes like because mean energy is proportional to n, so then this heat capacity, and heat capacity is proportional to this variance. So the variance has to be proportional to n, the number of subsystems. That is, we can say the fractional fluctuation of energy, which is the square root of this variance, divided by the energy, goes like square root of n over n, and which is basically 1 over square root of n. So the more subsystems we have in this, the smaller the fluctuation, the fractional fluctuation in energy. And that's very reminiscent of the central limit theorem we had back at the beginning of the course when we talked about random variables. The other thing we note, of course, is that this variance is proportional to t. If we just go back here, we see that the variance is proportional to t squared. So the standard deviation, the sigma of the energy fluctuations, are proportional to t. And so in a simulation, you could actually observe that if you change the temperature. This also tells us that, if n is very, very large, and macroscopically large, like Avogadro's number, then the fluctuations are very, very tiny. So this was one example, but it turns out all important quantities can be determined from this partition function. That's why it's such a useful thing to calculate. In fact, you might think that working with the probabilities is a very straightforward thing to do, but in fact that's quite cumbersome, and it's better to have this partition function z. So I'll have some other tutorial problems where we'll work with the partition function. Okay, well now we're going to move on to the grand canonical ensemble. So in the canonical ensemble, the number of particles or constituents or spins, like in our example, is fixed. And in many systems of interest, especially in quantum physics, and especially in the quantum systems that we'll study later in the course, one needs to consider a system in contact with a reservoir, which in addition to energy, the system can exchange particles with. So in this case, n is not fixed, and we need to we need to come up with, we need to generalize this approach. So we'll need to consider energy levels, which in general may also depend upon the number of particles in the system. So, for example, in quantum mechanics and other systems, if the particles interact, the energy levels depend upon n, and we have to sort of be a little bit careful there. So, an n-particle system, has a large number of levels. So, we'll first do the grand canonical ensemble in a very general sense, where we are a little bit careful about the number of particles and the energy levels, and then we'll show it's actually quite simple. It becomes much more simple when we have non-interacting particles, and that's what we'll consider in a lot of examples later in the course. So we'll need to specify the probability for the system to have energy epsilon when it contains precisely n particles, and we'll have to come up with the probability for this. That is, we'll have to write the probability of having n particles and energy epsilon. And so given the n, the epsilon will have to take on a range of values. Okay? Yeah, as I said, for non-interacting particles or constituents, this will be relatively simple, as we'll see at the end of this, later in this lecture. Okay, so the idea here is the system will be in contact with a heat bath, that's a little typo, that also acts as a particle reservoir. So we'll need to find this probability in terms of energy levels, epsilon, temperature, and chemical potential. So we'll have to add another variable here, the chemical potential. So the chemical potential, like the temperature, is an intensive state variable. Okay, so here we go. Now the derivation is very similar to the one for the canonical ensemble, so you can review that if you like. But we'll consider a small system we call A that's in contact with a very large heat bath / particle reservoir called A prime. And so this system A can exchange energy and particles with this heat bath particle reservoir. That's the idea. The derivation is very similar. So we suppose that our system of interest, the small system A, contains definitely n particles and has energy epsilon. Then the energy of the combined system, that's A plus A prime, we'll call it E0. It's the energy of the heat bath reservoir, E prime plus epsilon. And we'll consider it fixed in some interval, as you did in the with the microcanonical ensemble, and that will give us a number of states accessible to this combined system. That's why we consider some interval, and we have some number of states that the system can be in. And the total number of particles, of course, in 0 will be n prime plus n, and that we'll consider that to be fixed. So if A is definitely in microstate specified by n and epsilon, then the number of states accessible to the combined system when A is definitely has n and energy epsilon is just the number of states accessible to the combined system at, oh, I have a typo here, this should be E0 instead of U0. I will fix that when I upload the PDF for this. Anyway, it's the number of states accessible to the system with the combined system having E0 minus epsilon and N0 minus n particles. Yes, that's now understand that's the number of states accessible to the combined system, because system A is definitely in the state with n and energy epsilon, and this is the number of states. This multiplicity here are the number of states accessible to E prime, because the combined system is definitely in a definite state. A is definitely in one state, and so the number of states for the combined system is just how many states the reservoir can be in this situation. And so the probability is going to be proportional to this here, this omega prime, which is a function of E0 minus epsilon. I have it correct here. E0 minus epsilon, N0 minus n. And that's going to be some constant C prime times this. If we to go to the equal sign, we have to normalize this, and that's what our C prime is, which in principle we can normalize, which we'll do. So we'll expand this omega prime, or we'll expand the logarithm of omega prime as we did it for the canonical ensemble, and we'll expand it around the energy E0. So if E0 is much, much larger than epsilon and N0 is much, much larger than N, we can expand the logarithm of this quantity and just take the first derivatives, the first two terms actually in the Taylor series expansion, the power series expansion, and they look like this. And the derivatives, of course, will be beta, and we'll call this one for now, we'll call this derivative with respect to n prime alpha, and these, of course, are evaluated at E0 and N0. Well, let's just write this again on this page. So we did this expansion, and we identify these derivatives. We'll call this beta and alpha. And of course, you remember, or you can look in the beginning of this course, you had the fundamental relation of thermodynamics in Chapter 3, where you identified the derivative of entropy with respect to number, which is, of course, this, as minus mu over T. And such that basically alpha, that what we called alpha here, is minus mu over T. And so, of course, we know what beta is as well, 1 over kBt. And so we find that this probability is some constant, some normalization, times an exponential minus beta times the quantity epsilon minus mu n. Okay. Well, of course, we find the constant c by normalization. It's 1 over this, what we will call the grand partition function, and we'll write it as this z with a sort of blackboard bold z, this kind of z, grand partition function, or we can call it the grand sum as well, and it's a sum over the n particle states and their energies of this factor here. Well, similar to what we did with the partition function from the canonical ensemble and the Helmholtz free energy, we can define what we call a grand potential, this capital omega sub g, and we'll define it by saying that the grand partition function, or grand sum, is the exponential of the minus beta times this grand potential, or in other words, beta times the grand potential is the negative logarithm of the grand partition function. And in a way similar to the canonical partition function, we can determine important quantities in terms of derivatives of the log of the grand partition function, or equivalently the grand potential. So for example, it's quite easy to see that if we take the negative derivative with respect to beta, or partial derivative with respect to beta of the logarithm of the grand partition function here, it's quite easy to see you will get the mean energy minus mu times the mean number of particles. Now, this expression for the grand sum, or grand partition function, was quite general. I mentioned that we needed to consider the energy, we needed to sum over the energy levels for a specific n. And that's quite general, and the way we wrote it is quite general. In the case of non-interacting particles, it can be a bit simpler. And so this sum, then, if we write it in terms of non-interacting particles, then the energies are additive, and we can write it in this form. We can sum over n1, n2, all the way up to, say, some nr of these terms, where we just add these factors. And here n1 then is the number of particles in state 1. They have energy epsilon 1. N2 is the number of particles in, state 2, that should be 2. State 2 having energy epsilon 2, and so on and so forth. So we could write this equation again. We can rearrange it a little bit. We can separate out these factors, and we can write it as a product of these different sums, which we write here as the product of these sums which you can think of as a product of partition functions of corresponding to the number of particles in each level. So this is sort of like a grand partition function of where we've just summed over the number in state 1 and state 2 and all the way up to some number of states, z sub r. Okay, so it's much more simpler to write this and work with of course, grand partition function for non-interacting particles. Now, we'll see later in the course that the values taken by these number of particles in state 1 and 2 and so forth depend on whether the particles are fermions or bosons, as you might suspect. It's also quite easy to see from this expression that the mean number of particles in state R is given by the negative derivative of the log of the partition function with respect to epsilon sub r times 1 over beta. And since these are products, you can see it's just, we can find the mean number of particles in state R just by taking minus 1 over beta times the partial derivative with respect to epsilon sub r of the log of the grand partition function for state R. And that's very useful. Okay, so that concludes lecture number 5. I will come back with you next week with more lectures. Until then, stay safe, stay healthy. Hope you don't get too bored sitting around. Go over the lectures, take a break every now and then, and yeah, we'll see you next time.